Digital twins is one of the important technology concepts in Industry 4.0. Traditionally, manufacturers have used many proven methods and technologies, and in fact, management principles to improve quality, cost, productivity, cycle time in manufacturing. I mean, just like total quality management, kind of emphasis on physical processes and then training people. All those are still important, but as we talked about, some of the emerging technology trends are actually building new capabilities or bringing new capabilities to the manufacturers that they can completely reimagine how they would manufacture products and how they would service the product and how they would engage the customers and so on. So digital twins in that context is one of the important technologies. In short, digital twins actually brings together the capabilities of IIoT applications and that we talked about in the earlier course, and then the capabilities for simulation and modeling in a digital format, and putting it all together, it actually brings the possibility of a pure virtual product, a virtual version of a real product, and with this virtual version, manufacturers can do so many things like simulation, what if analysis, getting real-time information about how the product is being used by the customers or how it's being manufactured, and then work on that data, draw insights from data to further improve the product and customer experience. So that's the summary of what digital twins are, and we're going to be launching into this course, talking about various aspects of this technology, and this technology actually kind of can bring together as complex products as an aircraft. You can have a complete digital version of a physical aircraft, and that opens up so many possibilities for improving the overall manufacturing operations. Our broad learning objectives in this course are we'll focus on what are digital twins and how do they work, and then how does digital twin get successfully implemented, because again, this is, while the possibilities are great, but the implementation can become complex and manufacturers have to be careful in terms of how they navigate that process. And we will talk about the broad business advantages. What are the kind of business value propositions of this technology coming to the manufacturers and the various stakeholders in the ecosystem, including suppliers and customers. We would address some of the risks and challenges that comes with the technology. And finally, we'll kind of spend some time talking about the future trends that we can expect in this technology. Our mode of delivery in this course will include video lectures, just like what we are doing now. And in addition, we'll have additional case studies for reading materials. We'll have reflection exercises, assessments. In addition, we'll also have some leading industry experts who have been generous to donate time and join me in a conversation for us to learn about digital twins, this whole technology and its applications. And some of the experts who will be joining us are the following. We have Dr. Annie Zhang from Ford Motor Company. She's the Digital Innovation Specialist in Advanced Manufacturing. We have Jayanta Banerjee, who is the Group CIO in the Tata Steel Group, one of the largest steel manufacturers in the world. And from Siemens, we have three leading experts. We have Kathleen Divok, who is the Chief Architect and Head of Global Architecture for MindSphere. MindSphere, by the way, is one of the very popular platforms from Siemens that is used by many organizations for both IIoT applications and digital twins applications. We have Nash Chakraborty, again from Siemens, who is the Senior Director for Global Market Development and Cloud Applications on MindSphere. Finally, we have Stefan Jakush, who is the Vice President for Strategy at Siemens. Let us now understand what are these digital twins and how do they work. Well, a broad way to understand digital twins is they are actually a virtual replica of the physical product. What you see in this picture, on the left-hand side, you see the virtual product, which is shown in green. And then on the far right is the physical product, right? You can think about a car or a plane, any of these. Then there is a physical product. And then if you can collect data continuously on a real-time basis from that physical product to keep the virtual product of this version live, in the sense that you could actually, if you're doing a product, you could actually start with the design, which is digital, and then you create the product, and then you start collecting information from the physical product. So it's basically the virtual product, is a replica of the physical product and constantly interacts with the physical product and its environment around the physical product to collect information and exchanges data. So in the process, you understand about the real status of the physical product, and also you have the opportunity to inform the physical product as well and improve sometimes. So the process of both informing the product and the physical product and also accessing information is important, because you'll see, as we'll talk about more examples of digital twin, there are different levels in which you can actually kind of implement these digital twin. And the kind of data that is collected from the physical product can kind of span across multiple varieties of measurements in different dimensions, kind of through many sensors that will be attached to the physical product. And sometimes you also collect information about the environment around the physical product. So you can imagine, things like, as I gave the example earlier, that we could also say you could create a digital twin of even an airplane, a complex product for airplane. But to further understand why digital twins and what does it really mean from manufacturers and customer standpoint, let's start with a simple example. Okay, let's start with a question like, what would it be, to kind of create a digital twin? Why will it be important for us to, create a digital twin of something like as simple as a Michigan coffee mug? Okay. So you have what you see here is on the left hand side, is the physical mug that we all use, on a daily basis, and let's imagine on the right hand side it is the digital version. Well, when you're actually designing this cup and and then you're manufacturing, right? So you can imagine the cup that gets designed, and then you get, you finalize the design, you agree with the, specifications, then you mass produce that cup, right? When you design the cup, you can actually capture the information in a digital format. So now, how can you what are the ways in which you can do digital twin in a coffee mug? So you could just do a simple static digital twin, as you see in this, in the left-hand side, where you just capture the design information of the cup in a digital format, okay? That's why I call static digital twin, in the sense you captured the shape of the cup, the material of the cup, all these things in the digital format. You have stored it, right? And there is a value to that too, right? And you can see on the left-hand side, once you have that, you can actually, with that digital twin, you can do a lot of information. You learn a lot about that cup, right? In terms of when you do the design, you can understand, whether the average person's hands will fit into that, with the handle. And then if the design is suitable for all the dishwashers, you can kind of look at all those possibilities, and whether the mug is or the cup is well balanced when you kind of put it there on the table. All those, whether it is insulated well. These are the questions we can actually answer, because we have digitized, we know the kind of material that is used, we know the heat properties of the materials, and so on and so forth. This is what I call a static digital twin, where you actually captured before you started manufacturing, you have the full design information, in digital format. That's a very simple way of, implementing digital twin. It still has its own value. On the right-hand side, what you see, what I call as the dynamic digital twin. Now imagine, we actually put sensors in this, in these coffee mugs, okay? And then there are real-time sensors, which actually allow us to kind of, access information, get information through those sensors, after it is being, the cup is sold to the customers and they are using it. Now here what happens is you have the capability to collect real-time information about the cup, in terms of you can have, how often is the cup used, how often is the, is the mug normally filled with, right? And what is the average temperature of the liquid, right? Do the people use it for cold liquid, or do they use it for hot beverage? What are they using it for? And also, they can track in terms of what kind of impact is the cup coming across, and how often is it if there's a breaking. All this information you could actually collect constantly from the physical product to the digital version. Now you can see that when you move to the dynamic digital twin, of course it's going to be more complex, it's going to be more costly, because I'm talking about putting sensors in the cup, right? And in the context of a coffee mug or coffee cup, it does not make sense, it may not make business sense for us to collect all this rich data. But you get the point. As the more sophisticated, more features we put into the digital twin, we can get more richer data, and that data could be very useful in the context of manufacturing, but probably not in the case of CUP. Now, there are also other applications where digital twins is the only option because it is physically impossible for us to collect, data about the product or the environment in which the product is being used. One example here is the Mars rover or the Apollo 13, the NASA space missions, where you just can't collect the information about the physical product as it's being applied or about the environment. The only thing you can do is that you can actually collect it through sensors and identify what's happening in the digital twin version that you have here on the Earth, and that's exactly how they manage. So there are examples where digital twin is the only option. So that gives you a sense of what are the kind of capabilities of the digital twin as a technology. From the simplistic example of a coffee mug, now let us understand digital twins as it is used in real manufacturing. Let's look at this video, which actually shows digital twin of an electric motor in action.
Digital twins, the innovation backbone of the future, delivering virtual representations of real-world products, systems, and cities. For example, the digital twin of an electric motor not only showcases form, but also analyzes functions, from the rotation of the shaft to thermal conductivity to data from sensors and beyond. What's more, the digital twin continuously evolves, thanks to the flow of data, user experience feedback, and new input, and it's greatly impacting development, production, and operation. In development, a product's behavior can be simulated and tested long before a physical prototype has been built. Siemens utilized the digital twin to develop a world record-setting electric aircraft motor that not only weighs 50 kilograms, but is also 5 times more powerful than comparable electric motors.
Now, what we saw in that video, basically, you could appreciate the granularity up to which you can connect data about the specific parts of that electric motor. And they are connected through sensors, and you can get real-time information as the motor is being used by a customer. You can get real-time information about the performance of the motor and all the other dimensions of the motor, right? In terms of, you can actually even predict so many things because you have a real version of the motor in place in the digital version, right? Because all the information is there. You have virtually, you can monitor how the customer is using, how often they're using, just like the example we talked about in coffee mug. So why digital twins in manufacturing, right? You got the understanding of how it works in that electric motor, but you can now imagine if you have the capability, certainly it has got enormous benefits for the manufacturer because it can provide value in multiple dimensions. Just to name a few, it can improve safety because with the digital twin, you can first, simulate, even before putting the physical product, you can simulate a lot of scenarios to make sure that the product actually works as it is designed for. And that's point number one. That even if the product is actually being used, the physical product is being manufactured and delivered to customers being used, you can constantly get real-time information. And a lot of times you can actually predict the process uncertainties, you can predict any deviation in process and the product performance. So you can kind of have an early warning that basically both helps manage uncertainties and also help improve safety. Of course, the real-time information, as you saw in the case of electric motors or in the case of a simple example of a coffee mug, the full transparency in operations actually gives a lot more control to the manufacturer to kind of monitor and operate. And if you recall the introduction of this series, I talked about the pressure for manufacturers as they see from the market is that consumers are now more informed. The customers are more informed. They're demanding this personalization of experience, right? If you recall in our discussion with experts in the manufacturing industry, they're talking about how the demand for personalization from customers is actually moving into manufacturing as a capability of lot size of 1. Now, you can see that capability of lot size of 1 to some extent is now possible with the concept of digital twin because you're now able to have real-time information about the experience of each customer. You have real-time information about the manufactured product that goes to each customer, and then you can monitor and manage those, and hence kind of enhancing the capability of manufacturer to manage this lot size of one. Application of digital twins in manufacturing could be at a process level or at a product level. Now, on the left-hand side of this chart, you see what I call as a product digital twin. You have a physical product, there's an automobile there, and parallel to that, you see a digital version of the same automobile. That's a product digital twin. In a product digital twin, you actually collect a lot of product performance data. You can get information about design parameters, how they're changing when the product is being used. You get rich usage data, and you also can detect some faults that may be likely to be occurred, and that hence helping the managers to kind of design proactive maintenance and preemptive maintenance of the products. And those are some of the usages, some simple examples of the data that could come from product digital twins. And of course, a lot more, as you'll see in examples further down the course. On the right-hand side, what you see is the process digital twin. In other words, the concept of digital twin could also be applied to the processes. And for example, it could be end-to-end processes in a manufacturing shop floor. So you have several machines each stage, and all of them could be tracked digitally, and you could actually create a digital version of the entire manufacturing process. In fact, many, recently, a lot of modern manufacturing, even before they put the plant in place, even before they start constructing the plant, they create the full digital version of the plant with all the machines planned in terms of where the layout would be, how they would work. And in fact, they can actually simulate the entire factory operation through simulation to say exactly how it will work. And in fact, they may actually do some course correction in terms of changing the layout, changing the machines and things like that, so that they have a lot of analysis done even before they put any asset on the ground. And of course, once they have the asset on the ground, you can collect through the digital twin. If you make it active and live, you can have live performance data of each of the machines. You can have full transparency of the operations. And of course, you could actually detect if some machine is going to have any problems or already having some problems, and you can proactively take some actions. These are some of the benefits, and these are some of the data that you could collect to create a replica of the entire manufacturing process. The same concept is also used nowadays in construction process. The entire construction process, you could create a digital twin of the process, simulating different assets that come in place, and that actually gives a lot of opportunities, just like we talked about in manufacturing, about what-if analysis, and so that for the managers to derive insights. Annie, can you explain how the concept of digital twins is used in Ford? Give us some examples of the application of digital twins within Ford manufacturing.
So when we talk about digital twin, and digital twin is really the digital representation of a thing, right? The thing can be the vehicle. That is probably most people would think of when we talk about company. Or the thing can be the factory where we make the vehicles. So I think I can, because I'm from the manufacturing side of Ford, and Ford itself is in the manufacturing business, right? But I'm not in the product development at this moment. I'm more toward the manufacturing side of business. So I think it will be very good for me to explain what we're doing to build a digital twin of a factory. Mm-hmm. So again, what we try to get into is really the digital representation of the thing. In this concept, the thing is our factory. So if you walk into the physical factory, you probably will see a lot of machines, a lot of assets. We call those assets. And these assets hopefully are running. They're making something. So they're doing a certain jobs. Those jobs are processed in our definition. And going through those process, the end goal is to actually build up that vehicle. So quite often you see parts are being added to that vehicle. That is a product perspective of it. And you will see people working with it. And all of these exercise happen within workspace. It's within a factory with columns, with things like that, right? So what we are building is this digital representation of the whole factory, which has components of assets, process, product, people, and work spaces. Mm-hmm. And I know most people will jump into either the product or the asset right away because it's more meaningful. I would just take the asset as an example then, right? Yeah. So the example of an asset, a digital twin of an asset would be, I want to know everything about this asset when I'm at home. I'm not in front of the asset. I'm at home because it's digital. That's enabler. I don't have to be at home to get to the digital twin. I could stand right in front of the asset to see it. What we are gathering of this asset as an end result will include its operating or performance data. Is it cycling? Is it waiting for a job? Or is it down because of some problems? We'll get that right there. And also, we'll be able to see the history of all this performance. And given a station, what part is this particular asset making? Is it installing some bolts and nuts, or is it installing a seat? Mm-hmm. I will be able to see all those information because I have the digital twin of it. And if the machine, for some reason, is down, it will need someone's attention. And they look into that. You will need to do some physical inspection. And there's also a digital twin perspective of it to do it remotely. Mm-hmm. And from that angle, you will get into things that you cannot see. Your drawings on its maybe electrical control, maybe its drawing of its mechanical drawings or its hydraulic drawings. So that is the digital twin example right there.
Great, thank you very much. Yeah, and that was a very comprehensive answer, because I think you covered both the digital twin and the process of the entire manufacturing plant, and also you give examples at the
I'm a top-down person. I have to give you the context.
Very useful, because it is, you talked about how it could be used also and specifically in a particular product. Jayanta, certainly, I mean, you've discussed and you shared with us about your IoT infrastructure and very, very exciting examples with IoT. And we know that IoT is a platform on which you actually start building digital twins. So can you talk about the concept of digital twins, and more specifically, how have you used within Tata Steel with a specific example?
Yeah. So there is digital twin is another subject that it has, again, multitude of use cases, right? Because the concept is that you mimic. Well, I will become a little. I'll give you a spiritual example, right? Because this is something that I think, and I'm very. I believe that every entity in this universe is nothing but data. Because what I see, or when you are seeing me or I'm seeing you, it is my perspective and my perception. Something that I'm seeing, it is not physical. It is virtual to me. Right? Yeah. The set of data, how I look, what's your background, and all that is data. Right. So if I can have, say, infinite amount of data on you, or you can have infinite data on me, then you can actually really clone me, or I can clone you, or somebody can clone somebody. Right. So that's the concept. So the whole issue of digital twin is that we can take our supply chain and make a digital twin of that. What we have done in Tata Steel is that we have not done a digital twin for supply chain yet, but what we have done, but many other companies have done. What we have done, we have taken plants, operations, say a blast furnace, or say a sinter plant, or say a coke oven plant, right? And we created a digital twin of that. So that
for the entire plant.
For the entire plant. But say the coke oven plant, not entire Tata Steel. And there are 9 or 10 such digital twins we created. The person who is the supervisor of the plant, or the chief of the coke plant, can sit, and on his iPad will be the digital twin. All the decisions that he typically takes in at workplace, all the parameters that he checks, whether it's a temperature, pressure, vibration, XYZ sensor input, feedback, gauges, meters, everything that he checks, it's data. End of the day, it's the data. What typically a person will do, will go to the plant, go near the machine and check on the sensor or the meter reading. If I can bring it on the screen, then you check all the parameters and the correlation and the interrelationship between them on the screen and take all the required decisions. It is possible. It's very much possible. And that is what is called the digital twin, in my view. And you don't need to, I say steel is a very physical industry, and it's a mindset that if I don't go to the plant, I won't see the operation, I will not be able to handle it. But essentially speaking, are you really physically proximate to steel? No, it is a hot metal. You cannot even go near there. You're minimum 25 to 30 meters away from it in a control room. So if you are 30 meters away and you are watching from there, so if I put wall and put an HD television or a HD camera, and you get the camera feed and see better, you have a better vision, and we have done that. And then there was a huge adoption. There was a absolute no, I cannot accept it, because then there'll be catastrophe that will happen. And the same people who resisted, the operators, they wanted more, because now I can see better. I can find issues much early on. My visibility has improved, right? So all that happened. And then if you can move 30 meters, then you can move 300 meters. You can move 3,000 meters. You can go 30,000 meters. So it is all possible. It's a matter of mindset shift and nothing else. It is just, you have to just make it happen. Yeah. So the point is, a digital twin, when we are creating, there are challenges. The challenges are that the business will say that, oh, you have done 90%, but the 10% is left. Yeah. So you have to be very accurate, and you have to cover a lot of business process and a lot of operational process. But once you have it, the supervisory layer can be moved off-site.
Got it.
Without robotics and without autonomous operation, you possibly cannot move the physical work, the actual bulb change or the switching on and switching off. Those are controls. So the control layer will take a long time, maybe another 5 years, 7 years, whatever. And it will require possibly a socio-economic angle is also there, because it's not everything there is worker involved. If you're taking that worker's job, then it's not that he can be reskilled easily. So some can be reskilled, some may not be reskilled, and all that. So it is a mixture. So that aspect aside, the supervisory layer can be very easily handled through digital twin. The control layer will take a long time.
Kathleen, thank you very much for that example. I'd like to now follow up on the concept that IoT as a technology also more often used as a building block to building the capability of digital twins, and digital twin is a concept talked about a lot in the future of manufacturing. And I was wondering, Nash, could you give us an example of how IoT actually connects and creates its building blocks towards creating digital twin?
That's a great question, Dr. Krishnan. As you know, in Siemens, we talk about digital twin of product, production, and performance. And I can give you a great example of how these building blocks come together and IoT became a part of it. So there is a company called Konecranes. You must have heard about them. It's a company that specializes in the manufacture and service of cranes and lifting equipment. Now, this is a great example because they kind of adopted the digital lifecycle management software and the Internet of Things technology to bridge, as Kathleen spoke about before, the virtual and the real worlds. And the example is very interesting because the engineering and design group felt that most of their designs are based on engineers' experience and expertise on the product. And therefore, they may be over-engineering the product. So what they did is they ran the Siemens simulation software to measure to understand the various parameters like the torque, the weight, the stress points, the heat map, and the hotspots. Then what they did is they took that and actually put sensors in a real prototype that's in the field to collect the data from those parameter data from those sensors and bring that information back into the simulation design software and superimpose that with the simulated data. And this helped them answer several questions like, is the model correct? Does the simulated behavior actually truly represent the actual behavior? Is the design optimized or over-engineered, and so on and so forth? So this is a very interesting example where the MindSphere platform, the IoT platform, helped them in the digital twin of performance, bringing back the information into the product and optimize the design and the production processes.
So Jayant, that kind of understood. Thanks for sharing that example. I mean, that's a classic example. I mean, sometimes people look at digital twin that way, where you are remotely monitoring the operations, right? In a digital platform, sitting in your home, sitting in your remote location office, because you can have the full digital representation of the factory that is feeding in the real-time data from the sensors that I can actually see, or the supervisor, he or she can look at this data and then take decisions for remote monitoring. That's one side of the digital twin, right? One way of looking at it. But the other way also, like where we create a digital version of the particular product or a process, right? And before taking a decision, we can simulate an experiment, do some what if analysis in that particular case, and then see what the output is or what the outcome is in the virtual world, and then make a decision on the real world, right? That is also there, where you have a
that is there, and you're absolutely
Can you give
right.
an example of that? We use that.
Sure. You're absolutely spot on. So if you look at engineering and projects, that's an area where this can be done, right? Because it's a capex intensive project, you have to pump in a lot of money and to actually construct. So before taking a decision of a physical construction of an approved design, you want to see how it actually comes to life. So digital twin comes into the simulation that you said. You create the simulation and you advance the project 6 months. So it will look like this after 6 months. It will look like this after 18 months. It will look like this after 24 months, right? And you do that in a drawing room, in a boardroom or in a conference room, and you see that, okay, show me after 6 months what it will be. In a typical setting, you would give some presentations and discussion and debate, and it will go, everybody's imagination will go in different directions. Here, okay, this is how it will be after 6. This is a 6 months later image. This is a 12 months later image.
Got it.
This is a 24 months later image. So that is simulated by the computer, by the AI engine, looking at all the data. And then you say, oh, no, let us change this, right? You take the decision. And once then everybody sees and takes a decision, you go ahead and do the actual construction. So that's what is very much possible.
How do you implement digital twins, and what business value you can get from digital twins? It's a kind of it's an economic trade-off. It is about the how do you design the digital twin, what kind of information you collect, and also it leads to, of course, complexity in the digital twin. So it is important for all of us to understand, at what levels can we kind of implement this digital twins and what kind of benefits that we get. So here's a simple chart where I have two axes. The y-axis is the business value that you get from the digital twin, and in some sense, to understand the x-axis is the horizontal axis is the cost and complexity. So whether you can you can think in terms of the coffee mug or in terms of the electric motor, right? You can actually start with what I call a static digital twin, which is basically you design the product, you collect all the design data in CAD/CAM, and you can get in a simple digital twin format, and then put it all together so you have a digital version of the design of the entire physical product in terms of the parts that went into it. You can have a full digital version, what I call as just capturing the design data. That's in the green color. Now, you could also add to that, you can add into the design data what I call as the manufacturing data. Now, let's connect to the electric motor example that we saw. You have first the design data in the green color of the digital twin, where you have the design information of the electric motor. Now, in addition to that, let's assume that you start collecting information about as the electric motors are being manufactured. So the manufacturer actually kind of doing 100 motors and it's going to different customers. As these 100 motors are being manufactured, there are so many data, insights and information that can be collected during the process of manufacturing, right? For example, what is the serial number of this particular electric motor? Second, what was the kind of temperature of the alloy that is used to, kind of make the parts that is going into the motor? What is it? Some of the environmental conditions, like as the motor was being manufactured, this particular motor was being manufactured, and then who are the people working on it, right? You could also, collect the, that information. In which shift was it, was made? All this information you could have just kind of collected during the manufacturing process that could be added on to your design data, what I call as the design data plus the manufacturing data. So you see that the richness of the digital twin is going up as we kind of move from left to right. And of course, finally, what I call is the dynamic digital twin, which is the electric motor is now in the customer's premises, the customer is using, and we are collecting data. In addition to the design and manufacturing data, we are now collecting operational field data. So through sensors in the motor, let's assume we have all the right sensors as we saw in the video, we are constantly collecting this information. So we have a live version of the particular motor being used by the customer. Now, as you can see from left to right, the richness of the information now starts giving us a lot more contextual data and also more insights, right? Now, in fact, if you see here, the cost also goes up because from left to right, as I said, the cost and complexity, right? It is you're spending more. It is a complex digital twin, but you have to make sure that you have the right business value that you're deriving for that particular product. Like the coffee mug, it doesn't make sense to make the red color of a dynamic digital twin, right? You may probably at the best make a design data static digital twin, but in the manufacturing context, what you see in that arrow, what I'm calling is the criticality of the part, right? A lot of times when a part is very critical, right, in a product, then they sometimes, it makes sense. It makes a business sense for you to create the live dynamic digital twin where you want to collect as much information about that particular critical part as you can so that you can manage effectively. So let's so in summary, the green one is just the simple design data. Yellow is the design data plus manufacturing data, and the red is the full dynamic digital twin, which includes operational field data. And now you can connect back to the lot size of 1 or the customer experience of n equal to 1 we talked about earlier in the course. It is the red digital twin that actually gives the real-time connection for the manufacturers with the customers and the product so that they can do this both lot size of 1 and managing the customer experience at one customer at a time. Let's now understand the same chart in a different example in the context of an aircraft propeller. Now, as you know, aircraft itself is a very expensive product, and then propellers are one of the critical components. I'm just taking this example to explain that you could first start with the green version of the propeller digital twin. You will just have the design information about the propellers, right? And the yellow version will be design information of the propellers, plus you'll have all the manufacturing information. When was it made, which factory, which shift, and what is the temperature of different metal alloys that was used, and then what is the kind of environmental variable, what are the parameters in the machines that are actually making some of these propeller blades. So those are the information that you would collect in the yellow one. And of course, the manufacturing information is also important because it is important for you to track if you have any problem, say reported from the field, then it is important for you to track from that particular serial number of that particular part where it was manufactured, when it was manufactured, right? And what are the other what are the other manufacturing parameters in terms of, who was at the shift at that time? What are the other, parameters of the machines that are being used even before and after this part was made? So you get information to that level of details, and that can help you in troubleshoot problems. It can also help you in managing warranty. And of course, the red, piece here would be you have sensors on these propellers. You know exactly how fast they're spinning, what is the wind speed they're going against, and all those usage data that can derive some rich insight for the manufacturers to manage this entire product using digital twins. While talking about the business trade-off and the economic trade-offs and taking decisions around digital twins, manufacturers don't have to do digital twins for the entire product. In fact, what I call as the cascading digital twins, right? I mean, you could just do a digital twin of a particular part, and if you think that part is pretty critical, you could actually do a full dynamic digital twin. You could do a digital twin of a component, which is a collection of parts. Or you could do a digital twin of the entire product. And of course, as you can see, you move from a single part to a component to a product, complexity goes up, the cost of the digital twin also goes up. Similarly, you can have cascading digital twin in a process. Imagine a manufacturing process. You don't have to always create a full digital twin of the end-to-end process in a manufacturing, especially if you are an incumbent manufacturer, you already have plants. You don't have to have the full end-to-end digital twins, but you could actually start with digital twin of a particular machine being used in the manufacturing process. And you can actually digital twin at a substation level where there are multiple machines being used, or of course you can do digital twins and the entire manufacturing process end to end. So there are different levels you can actually apply the concept of digital twins. Today, we have Stefan Jakusch, who is the Vice President Strategy at Siemens Digital Industry Software, and industry experts with decades of experience working with large manufacturing companies, helping in the digital transformation. Welcome, Stefan.
Thanks for having me, Dr. Krishnan.
Stefan, I would actually start with the first question. We are talking about the concept of digital twins. So this is very popular. It's being very widely used now. How do you explain digital twins to someone who is not familiar with it?
I would probably use something that most are somewhat familiar with. Like think about a flight simulator or one of these race car simulators. You can sit in a mall and run a race. So these things really give you an opportunity to experience a very large, complex, expensive machine very realistically, to experience how it behaves. And you can even sit in that machine and you can check and verify that it works exactly the way it's described in the manual. You can check against what it was designed for. So if you take that idea and you translate it to the world of creating products and manufacturing, this is really the idea. You have a way you design a product. Today you do this completely in the digital world. And then you have a way to simulate every aspect of these products, whether it's the physical behavior or it's the way that air flows around it or any other aspect very realistically. So as a designer, you have a way to check whether your product meets your requirements that you started out with. Or if you go to the world of production manufacturing, you can actually build your manufacturing line completely and you can run it. You can even put simulated humans into it to make sure that they don't have to lift a weight that they're not allowed to lift and so on. So you can really build and validate your whole process from design to manufacturing completely virtually. And of course, that means whatever you do virtually, you don't have to do with a physical prototype. In the example of a flight simulator, you don't have to rent a plane and pollute the air with all the fuel and so on. So you can be very environmentally friendly, very efficient, and very cost efficient by using the digital twin.
Stefan, as we understand the concept of digital twins, I mean, we look at while the term is very broad, but the application of digital twins, I see it in kind of multiple stages. One, the kind of example you gave where you could simulate a particular design, either of a product or a process, and then, do a lot of what-if analysis and then freeze that design. That's one area. You could also do, digital replication of making a product in the assembly line, and then there is this digital replication of the product, sending it to the field, and in real time getting information through sensors on the health of the product or whatever the dimensions or what are the metrics we need to collect. Would you agree with this characterization, or how would you add to this?
So those are kind of the stages. It's interesting also to think about how this can evolve once you have all these three stages in operation. So imagine you have a simulation model that is very accurate. And of course, you have a manufacturing process that you have successfully replicated in the virtual space. And then you also have a way to capture data from your product in operation. There's actually some newer concepts that make the sum of these three things even more powerful. And we call them the executable digital twin. And the idea of that is that you take your simulation model of something and you integrate it into the final product. And it can do things like, for example, creating what we call a virtual sensor. So imagine you have a vehicle on the road and it measures, of course, your driving behavior, your vibrations, but there are things like the inner temperature of your cylinders in your engine, things where nobody would afford to put a sensor, but with a good enough digital twin of the product, you are actually able to predict or to estimate things like the inner engine temperature and stuff like that by actually running a simulation in real time on your vehicle. So these are kind of newer concepts where you bring the digital twin of the product in operation together with the digital twin that emerges in the design and evolution. So that's the only thing I would add. Outside of that, these three levels or three stages are perfectly accurate in my view.
So basically you're saying based on the parameters and the metrics that you're getting, you can actually create a virtual sensor as if the sensor was inside the cylinder, right?
Correct.
Stefan, I would like to now, move to some practical examples where you can pick, one implementation of digital twin, either, within Siemens or probably, with one of your customers, where you can explain to us what kind of these, which of these three stages we talked about, where the digital twin concept is applied, and what was the end result.
Yeah, it's hard to pick because I don't know any industry where this is not happening to some extent. This really has evolved. But if we take one of those who probably have been very much involved, and since you're in Ann Arbor, in the Detroit area, I think it's fair to look at the automotive industry to really have an example and the evolution that happened there. So where it started is there was always a mock-up. Going decades back, there was a mock-up, which is a physical model of the design of a vehicle. And the first stage was when this became a digital mock-up. So that was the first time where people were able to look at the vehicle, all its parts on the computer screen without building a physical mock-up. And if you look at a company like Ford, one of our customers in that space, they actually talk about a functional mock-up. So they moved from the physical mock-up to the digital mock-up to the functional mock-up. And then you ask yourself, what is that supposed to be? What they mean by that is that where a digital mock-up only shows you the geometric shape of every part in your vehicle, the functional mock-up really allows you to think like I'm going to mock up the function of seating or of normal driving or of an autonomous function of lane departure control. That is a function. And the idea is if I'm able to have a mock-up that represents that function, that mock-up is actually the combination of the driving behavior, of the physics of the vehicle, of the software running it, of all the sensors playing together with the physical hardware. So it's really everything we talked about, where it becomes bigger and bigger and more comprehensive. And it's something that again, it's an evolution that really is necessary today because every product we touch is usually a combination of sensors, electronics, and a complicated mechanical part. So maybe I hope I answered your question here, but that to me would be a very good example of how this also evolved over the past 10 to 20 years to become something much bigger today.
being in Michigan, we would like to, of course, talk about auto industry. And there are a variety of applications of the digital twin concept in auto industry. I mean, we talked about the product and process digital twins. All these can be applied, and there are so many applications, there are possibilities, and they're already being used by auto manufacturers. So let's see some of these examples. On the process digital twin, you could actually simulate the entire testing process, the test track process, virtually for the vehicle to be kind of tested, both on the virtual track with the virtual vehicle. You can have all the simulation possibilities so that for the engineers to understand, what needs to be corrected. And then you can have, a digital twin tracking. What you see in the lower part of this chart is the physical car that is being tested on the test track, but the the digital twin or the virtual car is basically collecting all the information about how the physical car is behaving, so that the engineers can get further insights for improvement. You could have the product digital twin concept used in multiple ways. Here are some examples where, on the top of this chart, you see, you're testing the physical vehicle and you're testing the performance and impact on certain parts. It could be brakes, it could be shock absorbers. Through the digital twins, you can exactly see what is the impact they're getting and then analyze all these parameters. And you could also use, as you see in the bottom of the chart, digital twin concept for sensing the environment around the vehicle, right? In this case, they are looking at the lane markers on one side and the distance from that. So the digital twin concept can actually collect the information through the cameras in the vehicle into the digital twin example of how exactly the vehicle is surrounded by the environment. Of course, the concept of digital twin is widely used in testing autonomous driving, right? I mean, which is a very, very popular concept now, self-driving cars. And many auto manufacturers are working on this new concept, from Tesla to all existing automobiles, whether it is BMW, Ford, or GM. All these companies are invested heavily in this. But I just want to emphasize how the concept of digital twins is used in testing, autonomous driving. Of course, what you see in this chart on the left-hand side, top left-hand side, is the autonomous vehicle test track. In fact, we have one here at the University of Michigan, MCT, where a consortium of auto manufacturers come and test their autonomous, driving capabilities. So when you start with autonomous driving capability, of course, when they start testing this, they would start testing in full virtual environment. They would like to get, the virtual digital version, the digital twin version of the cars, and put a number of those digital twin version in a virtual, roads, so that they can test. Because you don't want to first start with testing with physical cars, right? Because with autonomous driving, obviously during testing, things can go wrong, and you don't want to lose many cars. So they do start with complete virtual, testing, where it's all digital twins of cars that is being tested. Interestingly, what you see, in the third picture at the bottom of this chart is that when they start testing a real vehicle, so they created a physical car with all the features of autonomous driving, all the cameras and lidars and radars and all these in place. And when they are really testing in a test track, and what they do is that they actually first test this vehicle by putting it on the road on the test track and simulating virtual vehicles, simulating digital twin of other vehicles going in the road when this car is driving. So this car is actually testing autonomous driving, not with other physical cars first, but with virtual cars. So you can actually see how the vehicle behaves as other virtual cars come in place, because this vehicle is trained to detect the virtual cars that are coming. So the digital twin version of other cars. When they pass that test, then they actually bring some more other physical cars, which are either driven by real human beings, or they are driving on their own. So they put both a combination of physical cars being used, driven by human beings, or autonomously driving, plus they have some virtual digital twin cars as well in the road, and they simulate all these scenarios and watch how this car actually behaves in various conditions of whether it is taking left turn, right turn, parking, so many you can imagine the complexity of scenarios that are possible. They actually simulate all these things, and also in real time, once the vehicle is ready, they see how it behaves in front of a real vehicle driven by human being, real vehicle autonomously driven, and also other digital twin virtual vehicles. So you get an understanding of how they test autonomous driving with using the digital twin concept. So that actually gives you a summary of how the concept of product and process digital twin are used in combination to improve the entire manufacturing process and the product capabilities in auto manufacturing. We know that the focus of our course is on the business aspects of the digital twin technology. But I think for us to get a richer understanding of the business applications, it's also important for us to have some information about how this technology is built, who are the players, and what are the building blocks. So we'll spend some time understanding this. You may recall we talked about this, the platform architecture in terms of the different pieces going into the industrial Internet of Things, technology in our previous course. So this is what we talked about. We talked about how the security and cybersecurity and hardware communication infrastructure is very important for the IIoT applications. And we talked about the IoT platform and then the connectivity with the various devices, machine operating systems, and the enterprise software. In fact, the platform for digital twins often builds on top of the platform for IIoT, because as you can imagine, when we talked about the digital twin as a concept, it was it is working based on first static digital twin of digitizing the design information. As we move on to the dynamic digital twin, it is all about sensor technology, constantly collecting data, information, passing it on to keep the virtual twin more live as replicating the physical product. So in order to do that, you can see the role of sensors and the IIoT applications are right there embedded. So our digital twin platform actually builds on top of these capabilities of IIoT platforms. In addition to that, there are some new capabilities, such as the capabilities for modeling and simulation, like the capacity in these platforms to model various scenarios, various machines, and various operations, and also a capacity for simulations. Like they can actually do a lot of what-if analysis. You can different set of parameters and test in terms of how the particular process or product behaves. So those are the capabilities that come along with the basic IIoT capabilities on these new platforms. They also provide capabilities for contextual analysis of data and providing analytics based on the data that is generated from the test of these simulations, or it is also coming from live. So they have the capability to kind of derive some rich insights and provide the capacity for analytics. Of course, these platforms also connect with enterprise systems and in the manufacturing organization, and also the multiple devices, whether it is the field products or that is inside the manufacturing operation that you're trying to kind of mimic as a digital twin. All those interfaces are going to be important to collect the right parameters and right data that is required. In terms of the ecosystem of partners, again, there are some major platform players who actually bring this digital twin platform to the market. Of course, Siemens MindSphere is one of the prominent platforms where they kind of build both IoT applications and also digital twin applications across multiple companies. We have PTC Windchill is another PTC is another customer, another supplier of these platforms, and we also have manufacturing organizations have their own. Sometimes they have their own in-house platforms. They build GE Predix, and sometimes even system integrator organizations like TCS, Tata Consultancy Services. They have they've launched something called as a TwinX platform, which is a digital twin platform that they can build applications on top of. So you have platform providers, that is in the middle of that chart on the right-hand side of the chart, and then you have on the top is what I call as the system integrators, which we talked about again in the IIoT course. These Accenture, Deloitte, and IBM, Tata Consultancy Services, and many other companies. They're just a few I named, where they kind of bring this capability to work on digital twin applications along with the manufacturers. And a lot of times, many of these companies also bring their own platforms, right? We talked about IBM platform in the case of IIoT. And again, similar to our IIoT examples, we'll see that these digital twin platform, the platform, software platform that enable digital twin applications. More and more, these platforms are also now being, moved to this hyperscaling cloud architecture from, Amazon like AWS or Microsoft Azure, so that it actually allows them to scale these operations, scale these applications to multiple locations, and also in terms of both in terms of the scope of the application and also the physical deployment of the application. I would like to now follow up on the concept that IoT as a technology also more often used as a building block to building the capability of digital twins, and digital twin is a concept talked about a lot in the future of manufacturing. And I was wondering, Nash, could you give us an example of how IoT actually connects and creates its building blocks towards creating digital twin?
That's a great question, Dr. Krishnan. As you know, in Siemens, we talk about digital twin of product, production, and performance. And I can give you a great example of how these building blocks come together and IoT became a part of it. So there is a company called Konecranes. You must have heard about them. It's a company that specializes in the manufacture and service of cranes and lifting equipment. Now, this is a great example because they kind of adopted the digital lifecycle management software and the Internet of Things technology to bridge, as Kathleen spoke about before, the virtual and the real worlds. And the example is very interesting because the engineering and design group felt that most of their designs are based on engineers' experience and expertise on the product, and therefore they may be over-engineering the product. So what they did is they ran the Siemens simulation software to measure to understand the various parameters like the torque, the weight, the stress points, the heat map, and the hotspots. Then what they did is they took that and actually put sensors in a real prototype that's in the field to collect the data from those parameter data from those sensors and bring that information back into the simulation design software and superimpose that with the simulated data. And this helped them answer several questions like, is the model correct? Does the simulated behavior actually truly represent the actual behavior? Is the design optimized or over-engineered, and so on and so forth? So this is a very interesting example where the MindSphere platform, the IoT platform, helped them in the digital twin of performance, bringing back the information into the product and optimize the design and the production processes.
Stefan, I would like to understand from you the ecosystem of digital twins, development, right? So, yes, we now understand the concept of what digital twins is, and basically we are creating this virtual, product of the real product. But how does it all start? Who are the players, and who are the players in this ecosystem? If I have to, experiment with digital twin in my company, what do I need to understand?
To that, I think can scale very much. So I would roughly characterize the ecosystem on, let's say, 3 levels. So the first level is all the many specialized software applications that play some role in a complex technology like automotive, like we just talked about. I once saw a report by one of our automotive customers, and they just counted how many applications they were using in their electronics and software development, and the answer was 247 or something of that order of magnitude. So there's lots of those specialized little applications in such a system, and they do one specific task. Then, if you go one level up, there's relatively few players who kind of create the backbone of the digital twin, which ultimately means bringing together in a large field like the engineering manufacturing space, bringing it all together and creating this consistency of workflows. And I can name the major companies here. I mean, one is certainly Siemens, Digital Industries Software. There is Dassault Systems. There is PTC to a lesser extent in the very complex industries like automotive. But all these three companies, I would say, provide the majority of solutions at that scale of providing the backbone. And then, of course, you still have a very complex IT landscape if you put these vendors together. So another level of companies who play a big role here is integrators who really don't necessarily develop their own applications, but they are really specialized on creating business solutions. And many times these solutions go beyond the engineering space. They bring together the enterprise resource management, when SAP, for example, would play, and they are the ones who integrate this into what ultimately becomes a very unique enterprise solution. And in this space, like Siemens has several strategic partners that we did a number of great projects with. I would mention Deloitte in that list, or Accenture is a strategic partner from Siemens. So that's, I would say, the third layer is those companies who then build very customized, very specific solutions for a certain enterprise. And it's really different by industry and by customer to what extent every one of these layers will be used and how complex it actually is.
I just wanted to follow up on that answer. That was very, very clearly explained, the three layers. We also now more recently hear about the IoT platform from major software vendors like your Amazon AWS or the Azure platform from Microsoft. How does that fit into this? Does it fit into this ecosystem of building the digital twins with the sensor network?
I would characterize the two you mentioned. We call them hyperscalers. That's another way they are called. And the reason they received that name is that their biggest unique strengths of all of these companies is to provide this very scalable, powerful platform where you can run essentially anything. So every one of our products, for example, can run on Amazon Web Services or on Azure and on others as well, like Alibaba if you go to China and you want solutions there. So they're fairly generic at that level. Now that said, of course, all of these platform providers, these hyperscalers, they all are in a direction, of course, to provide more specific solutions. I would say if you look at that space and you really try to understand the role of everyone, it's still the case that for these solutions, you need a lot of industry knowledge and understanding. And if you just look historically, Amazon and Microsoft, we all know what their history and their past is. So they come from a strong technology understanding and less of an industry insight and understanding. And I would say the direction of growth is to strengthen that understanding, no doubt. But there's still, I would say, a gap. And at Siemens, we created actually an IoT platform starting roughly 5-6 years ago. It's called MindSphere. And MindSphere actually uses the infrastructure of several of these hyperscalers. It's compatible with several, but it creates a layer above that is very specific to typical industrial applications where you have to do things like scheduling, monitoring, preventive maintenance, and so on. So it's a specialized layer. And you could say in this field, it's certainly a combination of partnerships and competition that's happening here, because in the same way that we use at Siemens, we use the platform of these hyperscalers, I believe someday we will be competitors for these industry-specific applications. It's a very dynamic field, and we will see a lot of evolution happening in the next couple of years here.
By now, we have talked about several applications of digital twins in manufacturing and also the different types of digital twins. Let's now look at the business value proposition and the business benefits of digital twin. We have captured this in a simple, five-dimensional framework. These are some of the important dimensions. There are more to it, and we'll talk about. These dimensions, as you can see, we can talk about digital twin benefits in terms of productivity improvement, quality improvement, cycle time, and of course, in terms of enhancing safety and compliance, and finally, about customer experience. Let's look at these, each of these dimensions one by one. On the productivity, whether you can take, the product digital twin or the process digital twin, the capacity to simulate, as I talked about in the manufacturing process, actually certainly reduces a lot of rework and hence improves productivity. And of course, in the case of process digital twin, it can also, significantly improve testing efficiency if you can, look at a particular testing process and in terms of what kind of defects are being, tracked in that particular process, and you can then proactively take actions to reduce that. And you can also do the testing with both automated information coming from the process and also in the product. You could actually certainly do a lot more testing with the limited resources. Of course, you can have the faster development process, product development process, because you can see the different stages of the product development. A lot of rework happens. Once you have the digital twin simulation possible, you can reduce those rework, and you can also reduce all the time in the handoff, so that time is kind of restricted, and hence leading to both productivity and cycle time benefits. And finally, in the case of product digital twin, we talked about real-time tracking of products, and that can have huge implications for both quality perceptions and also for warranty tracking, proactive maintenance of products, and so on and so forth. Okay, and certainly all these things are going to contribute to productivity improvement. On the quality side, we talked about we can detect the defects earlier. That means so we can actually track these process metrics, and we can even predict before the defect happens with digital twins. And but even if you find the defect, the process of digital twin allows you to simulate the situation, then identify the defects and correct the defects. So debugging of the defects of what is the source of the error, that can be easily tracked with the digital twins. And of course, you get real-time insights based on the actual product usage. So you have a lot more insights about why a particular defect is happening. If suppose the defect is happening in the field, right? So the field defects can also be managed much better way through digital twins, and hence the overall capability to simulate new changes, right, and defect corrections, that brings enormous quality benefits to the organizations. Of course, we talked about a number of the cycle time benefits, because reduction in each stage of the manufacturing process, and also reduction in the testing of the concepts to get new product development. Those can be reduced with this capacity for modeling and simulation that comes with digital twin capability to look at all the different what-if scenarios even before we roll out the final design of the product. And so that cuts down significant time in the product development. And of course, you have efficiency benefits to manage both there are a lot of times the way to understand these interdependencies, and especially in complex products, what you would find is that there are so many interdependencies across different components, different parts of a product. And those interdependencies, if they are not managed well, they certainly could be cause of downstream quality problems and a lot of other challenges. The concept of digital twins that we've been talking about, the capacity to simulate and model, allows the manufacturers and the engineers in manufacturing organizations to look at the various scenarios in which the part is being used or the component is being used, and then work out these interdependencies in a virtual format even before they put the real product or the part in place. And of course, the concept of digital twin, enhances the rapid response from the manufacturers to the customers, because if they have the real-time visibility, they can pinpoint and then find the root cause of the problem very fast. On the safety and compliance, we talked a little bit earlier, the concept of digital twins, the simulation, just like I talked about quality benefits of looking at the interdependencies of components. Like for example, in the aircraft industry, they first, they simulate the plane. They would actually virtually fly the plane, before putting real aircraft in the air, because you can understand the safety reasons for that. There's also a lot of compliance requirements, right? If you recall, we talked about the green box, which is a simple static digital twin with design data. Then I talked about the yellow box, which is design data plus the manufacturing data, right? Why that is important? Because in some industries, it is very, very important for to keep records of when exactly a particular part was manufactured and what are the other data around the process of the product when the manufacturing happened. Because that becomes very, very helpful when manufacturers have to actually track a particular problem from the field. A lot of times, manufacturing is a complex business, right? And especially when you're manufacturing, mission critical vehicles or like aircraft, even automobiles, right? I mean, there's a famous example. Many years back, there is one of the large automobile companies had a problem with the tires of their SUVs. The tire will burst randomly, and then of course it lead to fatal accidents, kind of creating certainly loss of life and also huge warranty and financial implications for the manufacturer. And the challenge there was they were not able to predict that particular problem, okay, because it is happening randomly, right? And so they were not able to track it because there is no visibility in terms of when these tires were manufactured. So in the concept with the capabilities like digital twins, now this manufacturer can actually track every tire. If some SUV basically rolls over because of the tire problem, then they can track that particular vehicle and then get the information about where the tire was manufactured. And the tire manufacturer can actually, with the digital twin, they know exactly this particular serial number of the tire, when was it manufactured, and then they can go to the root cause of the problem in terms of why the tires from that particular shift were defective. That's just an example of how it helps manufacturers to manage safety and compliance, and also respond rapidly to any warranty claims and get to the root cause analysis. Last but not the least, the customer experience. Now you can imagine I've been talking about in the Hexatech trends, the big technology trends, about the emergence of intelligence, embedded intelligence in products and process. Embedded intelligence is exactly what we're talking about in digital twins, right? Once you have the digital twin capability, this embedded intelligence in the products, then you have live information when the product is being used by the customer. Whether it is an automobile that you're driving, the auto manufacturer now may have the capability to track personalized information n equal to one sample of one, right? For every customer, they can get the rich information of that product that's being used. And that certainly then leads to proactive response to customers. Even before customer sees a problem, they can actually call the vehicle for servicing, and also, ability to real-time problem diagnosis, right? Sometimes, the cars that are digitally what we call as the connected cars nowadays, they are, constantly connected, to the manufacturer system. They can actually monitor, they can remotely service your car. All these possibilities are now, become a reality with the concept of digital twins and the broader Industry 4.0 digital applications. So in summary, we talked about benefits in productivity, quality, cycle time, safety and compliance, and of course, finally, the customer experience. But these are just some of the dimensions. In fact, another important dimension is making the environment green, like managing the carbon footprint, for example. Digital twin as a technology, as we talked about, increases productivity significantly. That's not just only benefit to the manufacturer, right? It reduces a lot of rework. It actually kind of makes it more efficient way to connect with warranty issues. So all these things also makes the manufacturer more green in terms of the carbon emissions from their operations. So these digital technologies have a collective contribution to make these manufacturers, kind of their operations environmentally more sustainable. We've talked about all the capabilities of the digital twin technology, and also we discussed the business value propositions. And these are pretty attractive, right? I mean, it may appear that, it's a no-brainer decision for all manufacturers to deploy digital twins in all places, but it's not as simple. Because these projects, around digital twin, creating digital twins, either in the product or process, these projects are pretty complex. They involve several technologies. They often involve multiple teams inside the organization. Of course, they also could be quite expensive depending upon the complexity of the digital twin that you're building. And hence, manufacturers have to take some right steps, and they have to have a disciplined process and capabilities in place for these projects to be successful and also scalable. So here we have a simple 6-step framework which actually can help manufacturers to improve the success of the implementation of the digital twins project or initiative. Number one is to identification of the problem areas, identification of opportunities where digital twin could be applied. Number two is building the capabilities within the organization, for not just one project, for multiple projects. Number three is how to manage sponsorship, how to identify the right sponsor for each of the projects. And then number four is alignment with the multiple partners, both internal, external, identifying the solution in terms of the specific features required and compatibility with infrastructure. And number five is, committing to partners and platforms, and then managing that ecosystem that they select. And finally, to execute and make these projects successful and scalable. So let's start each one of these one by one. In identifying, in this step, as I talked about, I think manufacturers can, constantly survey, the broad areas of problem areas, and, look for opportunities where digital twins could be applied as a solution, either in a product or process. And they can select a specific problem and then or an opportunity, and then decide whether what is the business case, what kind of digital twin will be a viable business case. Is it just the design information, the green one we talked about earlier, or is the dynamic digital twin, which is the red box with all the real-time data coming in. And of course, they can identify the type of digital twin and also the site for implementation to make it feasible and also increase the probability of success. Building capabilities, as we talked about this framework also in our IIoT course, it is important for organization to think this as a collection of capabilities and not look at it as one project at a time, but actually, pull together these capabilities in one, maybe a center for excellence for this technology. And probably companies can actually build on top of their IIoT, skills and then kind of the organization they have for that, because here you need to bring together the modeling capabilities and the simulation and some of more engineering skills coming in as you build the Digital Twins Center for Excellence. Next, sponsor. It is very, very important to identify the right sponsor here, because often the digital twin projects, whether it is product twin or it is the process twin that you're implementing, they are going to involve multiple stakeholders, right? I mean, in terms of internal processes, internal people, and also you may actually directly deal with customer enterprises. So it is important to kind of identify these different pieces, identify the multiple stakeholders, and also assign an executive sponsor, because it is important to give that support and cover for this project. And this project can actually can be risky at times, and actually can take longer than it is planned for, because you have to be pursuing with the project and giving it all the resources for the proof of concept to be shown. And then if the business results are viable, then it can be scaled. So for that, I think it is an executive sponsor who understands all the stakeholders, who is knowledgeable about the technology that is being built and the problem that is being solved, and is also willing to support and being a champion for the project. Then comes the alignment. There is a lot of various pieces of that needs to be aligned for a digital twin project to be successful. First, they have to think about they identified the problem, right? Once the problem areas are defined, then you finalize the granularity of data and the type of digital twin that you need, whether it is the static or the dynamic one. And also you need to decide what is the level of the component, right? You're going to do a digital twin for a part or a component, or similarly, if it is a process, what exactly are you going to, replicate in the digital virtual format? Then you uncover all the technology infrastructure that is needed, right, including your hardware, software. Because remember, digital twin, concept actually rests on the IIoT capabilities as well. So it has to be taken for granted that you have a high-speed communication network, the sensors work, and all the stuff. So it is important to have the infrastructure in place and then make sure that is there, and then assess the compatibility and the integration needs, right, in terms of when you bring together simulation and modeling skills that works with the sensor platforms that you have, to make sure that all these things are connecting. And also not just about technology consistency, right? It is also interdependencies in terms of process and people. So you need to identify the changes required in people's behavior, and also the people's skills required. And so broadly, it actually defines how the new process will operate. You got to kind of define clearly after the digital twins are put in place, first how it will work, the different pieces coming together, and how the new process and data will be operating. And that's how you need to kind of build this alignment broadly. And once you have this, then you can go to selecting, identifying the partners, right? And then you have to evaluate the ecosystem of partners, who are the platform providers, who are the system integrators, and what value do they bring in, what is the strength of the internal team, and then of course you select the right platform. And once you kind of have the right platform, then you also kind of start building this ecosystem with the internal technology team. Then one of the unique aspect of a digital twins project is that you usually have a pretty heavy involvement of the engineering and operation team, depending upon whether it is product digital twin or a process digital twin. And of course, you bring in the software vendors and the system integrators and different kinds of partners. You are building this partner ecosystem, and then there has to be this executive sponsor who's actually championing this, and of course start preparing for that change management, because a digital twin that you're putting a product or a process, it's also so it's basically a big change in how the manufacturing organization works, right? And this change could be the technology change. It is also a social change, and hence it is important to have this change management program, effective communication with internal teams, identifying who are the people affected, and communicating the same with them. That becomes important. So you need to start preparing for that. Finally, the execution piece. I think the execution piece is where you kind of start, the implementation, and then you have a proof of concept in place, and then you're putting it, in action. And you need to make sure that you have the proper training for the process, and the cultural change. The cultural change is important because, for example, I'm aware of a large manufacturing organization where they went with the digital twin of the process. That means, they could actually now monitor the process remotely, through the digital twin concept, right? I mean, but that, had that kind of the social impact was that we have a lot of supervisors who are very, very much used to being inside the plant, monitoring all the operations, and they are very proud of the job they are doing. But the digital twin concept actually, it's certainly going to make it easier for the job that they are doing. In some case, may also eliminate some of the steps they were performing before. So hence, it is important for the leadership and the project team to be aware of these changes that are coming in, and so that you can bring the new culture for everybody to understand the new capabilities that is coming in, how it can improve the quality of life for all employees. And of course, then you roll out the twin project, and especially in the case of customer premises or even internal projects, you evaluate the outcomes in the first trial, and then look at the business results, and then hopefully with a couple of iterations, you will be able to get to some success point. And once you're successful, then you think in terms of scaling the solution for to other multiple customers or places, and of course then you prepare for the next phase of the pilot. I think, in execution and also across all these steps, right? If you look at what we've been talking about, one of the critical aspects of the digital twins, especially in the product digital twin, you may also be involving, customer organization more closely, whether it's individual customers or the customer enterprise in this process. So that has to be thought through, because this whole team has to be an interdisciplinary team. You're bringing together the engineering team, the software team, you're bringing the operation team together. In this case, you're also bringing both customers, into the conversation, and that has to be thought through and managed carefully. I will now take our discussion to, we know the concept of digital twins, and you are applying this at the plant level. What would be your advice to, companies beginning to experiment with digital twins in terms of what should they look for in selecting a particular area, a particular project, and what should they be careful about? What are the risks involved here?
Depends, I should say. Because I know Ford well, and because I work for Ford, right? And Ford is pretty big company, and it has a long history. So some of my suggestions could be biased, just because the challenges we have is where we put our focus on. But if a company is not like us, I think I would say digital twin is it's the second step after your digital transformation. You need to go digital first.
Okay.
And Ford is at a very high level of digitization at this moment. So if your company has a good digitization effort going on, or it's pretty digital, you're in a much better shape. But if you're not, go do your digitization first. And it's a good opportunity for companies who does not have a digitization strategy in place to put in place such a strategy, because there's a lot of ecosystems or platforms that are available. They can address a wide range of scenarios or process from end to end.
Yeah.
And
so, can you just explain a little bit more about to get the digitization right, and also give examples of the platforms you talked about, which companies can look into for the end-to-end digitization?
Okay, so I consider product lifecycle management a little bit ahead of digital twin. When any company who needs to design something, make something, and eventually service or sell and service something would need to go through a similar process. If your deliverable is a product to the end customers, right? How do you digitize your life cycle of the product from concept to maybe toward service? Nowadays, there's a lot of ecosystems or vendors that can do the whole thing. You've seen Siemens doing that. You've seen PTC doing that. You've seen Dassault doing it. That the name goes on and on. I do not have a complete list of things, but those are major players in this field.
Yeah.
You start with one of them. They quite often come with a very comprehensive capability to take your product from concept to engineer to digital manufacturing to eventually to the production world. They will be able to extend their platform to help you to get into the IoT business and link that back to your digital world. Unlike Ford, if your company like Ford, where we have, I don't know the exact number, but it could be tens or hundreds of different systems that we need to connect data.
That's right.
That's our challenge, right? If you're in that boat, chances are you would not be able to find something that fits all of your need. You would need to be very solid on what you're looking at, what your current state is, and where you want to go to. And you don't have enough time to go to. And you might need a lot of money to get there. Knowing what you have and knowing where you want to go, and do your research to understand what's capable. And I think there's quite a bit of consulting firms that will be able to share their insights from working with other companies, similar to what company similar to what your company is. That would give you another, maybe a little bit faster or scope down of what you want, what technologies and companies you want to further evaluate. But just take my words for it. You cannot take any outsiders' opinions for it. You own your own strategy. You know it better. And this is not just technology. It is your company's process, your company's culture, and all that good stuff coming together. So by all means, what I'm saying is leveraging what you can, vendors, consulting companies, and whatnot, based on what your vision is, your company's vision is, and based on where you are and your current data strategy, and find out the best way for you.
Like any other complex technology, digital twins as a technology also brings its own challenges and risks. So let's look at some of the challenges that manufacturers are likely to face, and also kind of they should be aware of, and think about how to kind of counter them. The sources of the challenges are the following, and we can start with first, scaling the technology outside the proof of concept. I think a lot of times digital twin projects, it is quite possible that they actually stay in the lab, in the sense they build a prototype, they build a concept, and then it works, and then it's not scaled. There are multiple, challenges that are faced in that context. One, they may not have estimated the cost, or they may not have captured, the level of granularity of the digital twin, the data for it to be useful to kind of, make the business case. So it is important for organization to think through this challenge of that the project does not get stalled at the concept and the pilot stage, because they need to think about scaling right at the beginning. So that's one of the challenges. The second challenge is the brownfield implementation. Now, often, manufacturers, especially this is true with the incumbent manufacturers who have been in the business for decades, right? I mean, they may have infrastructure that are not modern, and in that context, they often think what I call as a brownfield operation that's been there for many years already. They may think that they are not modern enough, and that these technologies may not work for them. Actually, that's quite to that contrary. I mean, digital twins can be built by kind of customizing interfaces to existing machines. There are organizations which have actually kind of implemented brownfield implementation of digital twins. Well, it may not be 100%, kind of full dynamic digital twin, as we talked about the different stages, right? But you can certainly reap certain benefits of digital twin, even if you're a brownfield operations with, probably older machines or things like that. So you can think. So the company should not be kind of dropping just because they are it's a brownfield operation. It is not. This digital twin technology is not only for the greenfield platforms. So the next set of challenges is stems from talent, right? Sourcing the right talent. As we discussed before, all these Industry 4.0 technologies on these projects, they require talent, from the engineering side. They require talent or manufacturing and the operation side, and also they need software talent. So you're looking for this, interdisciplinary team, and also you have looking for talent. They have kind of they're good in multiple areas like business, technology and operations. So there is going to be premium for talent that understands both business operations and technology in this context. So it's important for manufacturers to both locate this talent, nurture the talent, in some cases upskill the current talent that they have. So they have to manage this and then connect back to what I refer to as a Center for Excellence and for digital twins. It has to be linked back to that. And the last piece of challenge that I have here is related to both the technology infrastructure and the social infrastructure, because on the technology infrastructure we understand, right? There are kind of variety of platforms here, variety of machines, and they need to be connected, and companies have to think through that. And also equally important is the social change, like the couple of examples, and I referred to it both the technology and social earlier. This is not only a people technology change, and in order for firms to get the benefit from digital twin in operation, they need to put the social behavioral change. They need to prepare the stakeholders who are getting affected by these operations. Because if you totally automate monitoring of a plant, of a product, right, that means you are actually redefining current job roles that are existing. So you need to prepare how do you kind of tackle that, how do you kind of communicate, how do you upskill, how do you redeploy your resources so that overall the benefits from these technologies goes to everyone. Next, let's talk about the sources of risks in digital twins, right? Certainly, the first risk I would say is the costs, because these projects could become very expensive. So that business trade-off has to be analyzed very carefully, and also that executive sponsorship is required because they need to know that we are in this for a long term, and then they should be ready to invest, especially if they are building a complex digital twin capability. The second risk is sometimes companies, don't make the right choice of the granularity of data that they need in the digital twins. As we talked about, there could be different levels of granularity, right? If you recall that chart that I was talking about, green, yellow, and red. I mean, so depending upon the business case, you have to pick the right level of granularity, and that's a risk. And if they have that choice wrong, that's one of the reasons then the pilot may actually stay in the lab. And of course, cross-functional alignment is a risk, and this digital twins initiatives are bringing together products and people from multiple functional areas, and that's always need to be managed because it's not easy. That's where the next risk comes from leadership and change management. I think if you don't have the right leader, if you don't have the executive sponsor, and the project leader who are well-rounded, who understand both the technology and the social changes that are coming in, and then proactively prepare for that, that could be a big risk for the project. And the last but not the least, in fact, one of the most important is the cybersecurity. Because with the digital twin, while the capabilities are so attractive and then and that makes the opportunities more versatile and so many things that can be left only to imagination what the manufacturer could do, we should not forget that when we move the entire product, a complete digital version of a car or a plane, that means they are also open to be hacked, right? They will be open for for cyber threats, right? And that's why cybersecurity is a big risk and has to be proactively managed by the manufacturers if they are going seriously into digital twins. Stefan, based on your experience implementing, many applications of digital twins and other digital technologies in manufacturing with your clients, specifically in the context of digital twins, what are the challenges that your customers face, that you've seen your customers face as they try to roll out, digital twin technology, or they try to experiment with implementing digital twins?
The biggest challenge is probably the idea of experimenting. And that may sound crazy, but let me explain. The digital twin is a big opportunity because it opens the possibility to transform processes, to transform how a company operates. And I think the biggest challenge is if it is looked at as an incremental technology, as something incremental that leaves everything intact, but just turns a few things from hand drawings or physical into virtual, it's a big opportunity missed. So I would say in every industry, we find great examples of transformation and of becoming 10 times more productive and cutting costs by 80%, 90% rather than 10%. And I think so that is when it really pays back, and when the investment that everybody has to make into transforming really pays off. So if you ask me for the biggest challenge, I would say the biggest challenge is, or the biggest risk is missing this opportunity to really step back and rethink how a business operates in the context of introducing technologies for the digital twin.
I mean, it makes a lot of sense. Now, the way you put it, to me, I think what you're saying is it's the mindset of the managers. It's the willingness to experiment and try. That is the biggest, obstacle to cross. I would assume that a lot of that maybe is driven from what I would call as the myopic cost-based kind of view, where people look at this as a very big high investment, right? Do you see this sometimes, and how do you recommend people overcome this?
Certainly, first of all, it always looks like an investment, and it looks like an investment on top of a cost base that is steady. So it looks like spending more money. It's an initial stage, always looks like it. So as I said, you have to have a very strong vision and a mentality of not experimenting, not dabbling, but transforming to really see the end of that journey. Because at the beginning, it's an additional investment, and you have to have this end in mind where you really work completely differently. And the second factor to overcome is the risk, the fear of taking risk. And I give you an example. We've talked about automotive before. In automotive, simulation really has progressed much, much slower in its use than the technology was really allowing. And it's simply because managers who are responsible to launch a new vehicle, they would say, what, you're telling me you want to do this with 20 hours of road testing where we did 200 hours in the past? I'm not going to take this risk. That is the first obstacle. And so it always historically has taken much more time to get to that level. If you look at some of our customers like Daimler today, so Daimler today validates and verifies the noise and vibration testing completely virtual for the majority of their passenger cars. And that was something that people would say, no way that we can do this completely virtually. Especially these very important things. As you know, in luxury cars, vibration and noise is super important. And nobody expected maybe 10 years ago that anyone would take this step to just say the whole new series of the C-Class, which is many, many variants, we are going to be sure that we are right on in our program completely virtually without any road testing. So this is always a big step. And that, to me, is the second thing that has to be overcome, is to really have get to this level of confidence that people say the digital twin really does its job as supposed, and it really allows us to reduce our physical or road testing effort by 90% or even close to 100% by virtualizing.
I would like to follow up, with another question that you just mentioned is the mindset and the ability to experiment and So building on that example of 200 hours of road testing to 20 hours, do you also see a risk from digital twins coming as a pushback from the labor reduction in the process? Is that an issue at all?
I have myself, in my past, I've been in situations where our own workforce was resisting virtualization and automation because of it. So I would definitely say if you go across, there is definitely that point. If you realistically look at it, I don't think we can always say people lose their jobs if we automate, but then you look at unemployment rates over time and you don't see that reflected. But I would agree with you. It's certainly a humanly understandable concern and a fear that people would say, yeah, if we reduce road testing, then our road testers will be out of a job. I think you and I know that in the longer run, this is never true. And it never turns out. I mean, before cars were here, we had horse carts, and we had lots of people cleaning the streets and scooping up the horse poop from streets. They are all jobless now because there's no more horse carts. Does anyone lose a job because of that? No. So I think it's not necessarily realistic, but I agree with you that it's humanly understandable and present.
Annie, let me follow up with that comprehensive answer with when companies get into a digital twins project, right? They identify an area, they get into launching a project. What are the risks that they should be aware of? Are there any risks that they should prepare for?
Absolutely, and especially if you look at a company as with the size of Ford. The risk could be humongous if we do not have a plan or on the lookout for it. I know this is maybe too old of a topic, and if I say it's just security, cybersecurity, but nowadays it's not just the data leakage. That is a very valid concern, because if all of your IPs reside on your data, right? So that one we all know. I do want to bring one particular example up in terms of risk. In my view, this risk has become more and more pervasive, and I think it deserves a lot more attention nowadays. Ransomware attack. It wasn't. I think we all know at the U.S. The fuel pipeline shut down because of ransomware attack. And I was the other day I was looking into what are the other things that might be still high risk out there, and I started with ransom. And for some reason, I have the ransom on my search. And when I bring it up last night, when I was trying to search for something else, the page stays there, and then you see what you can expect what happened. It was another ransomware attack it was a meat package company, I think. Ransomware is a means for people they halt your production, they halt your operation, and in return for money. If you give them money, they will release the halt, right? That is the ransomware problem. So we all know, if you Google how much time it costs if a phone shuts down for a second, right? So that is the high risk. If we are not careful and we got attacked by ransomware, that risk is huge. And it's really realistic.
Thank you. I think that is very, very important. And so the point is, you got to have the cybersecurity, and you have to have the steps to kind of counter all these attacks, and you have to have these capabilities in place before you invest heavily in digital twins. Thank you.
Mitigation, right? Quite often you cannot reduce your risk to zero. We have to take risk. It is a matter of we need to have a way, have something in place. If something like this does happen, what is our plan? We do not want to be reactive to such an attack.
Advances in the broader digital trends that we talked about, like whether it is sensor technology, whether it is artificial intelligence, and all these emerging concepts, right? They're all contributing to, in fact, shifting the capabilities and applications of digital twins. Let's look at what is the future of digital twins? What are some of the features that we can look at, and what's going on in this industry of platforms that are kind of producing digital twin capabilities? And here are some of the things that I think we can expect. We'll see more integration of voice, as we can see that instead of interface through a keyboard and a computer, and more voice becomes a standard expected way of interfacing with machines, and hence that'll move to digital twins as well, because digital twins in some sense are virtual machines, right, which are replica of a product or a process. Then we will also see more applications of machine learning and artificial intelligence coming into digital twins, where the twins may be able to do some predictive analytics. Without a human intervention, you can see the digital twin collecting the real-time data from product usage, may be able to predict a problem that is likely to occur. So you will see more predictive analytics being applied. And the third, we see that as digital twins become a critical capability, and that is helping manufacturers significantly improve their product, in some cases differentiate their product in the market. So there's going to be a lot of advancement in terms of improving the performance of the digital twin. Basically what I mean by that is the capability for manufacturers to simulate various scenarios to create a digital twin of a product or process. So in order to create that capability, I think there are advances in more dedicated chip technology, where companies would actually go for dedicated or customized architecture to build digital twins for a specific application, whether it is an automobile or a part in an automobile or any of those, so that they can enhance the performance and improve the accuracy of digital twins. And for that, they need a high-speed processing platform. So there are a lot of advances being done in that direction, because this technology, what they'll do is that then it'll customize the chips for those set of applications, hence making the digital twin capability much faster and more effective. Finally, I believe that I think we are moving into a world where there'll be intelligent twins working with humans and sometimes without humans also making real-time decisions, right? Because the digital twins will have enough information, and if the information can be captured in structured data, and then in terms of rules, then in terms of how the action should be taken, it is quite possible that digital twins would be taking some action. In fact, we already know, for example, when we say that an airplane is an autopilot, right? In some sense, what's going on is that there is an interface in the the virtual plane is collecting all the information and it's kind of taking decisions on its own. That's just a starting example of how the concept of digital twin would also be involved in real-time decision making. Stefan, can you paint a picture for us in terms of digital twins and the capabilities that we have even today is so impressive, but the technology is evolving so rapidly. Mm-hmm. Where is this headed? What can we expect in the next 3 to 5 years timeframe?
We are already starting to experience. And I told you, if you go back 10, 15 years, the focus was very much on the mechanical part of some of the products we have, because electronics was not so much and there wasn't so much software everywhere. Then it moved on to be more focused on electronics and of software. And we firmly believe at Siemens the next level that is going to become an integral part of this is the chip, is the integrated circuits. And you can see this already everywhere. First of all, more and more, I would say, classic manufacturers like car makers or airplane makers or even the makers of sports watches, of stopwatches, all of these companies now do chip design in-house. They consider designing their own purpose-built chips in-house one of their core competencies. And I think that's the next trend. And seeing how you more and more need these powerful chips that are also very secure, very safe, very resistant to harsh conditions. I think automakers, for example, decided in the old days we would give the job of designing chips to somebody outside of our four walls because they know this better than we do. Now they're more and more getting to the opinion there's so many things to know here about the use and so many specifics about what it needs to do. We need to make this our own core know-how. And I think that's the next thing happening. We will talk about the combination of the semiconductor level and electronics and software and mechanical. And the digital twin will have to incorporate this to create the benefit.
I'm just trying to understand from the chip point that you made to the digital twin. So the design of companies will try to own the design of the chips so that they know exactly what their application is to make sure that the chip is designed for that purpose, right? And number one, and also these chips will help them to mimic the product that they are making more easier in a virtual context. Is that the point?
Yeah, let me give you an example to make it crystal clear. So if you look at a modern car, maybe not a fully autonomous car, but let's take a modern car, a car that is able to keep the distance from the next car or to keep its lane. So that car already taps into cameras and sensors. And if you look at the process of getting there, there's a dedicated chip or a combination of them, a system on chip that is really handling all the data. So if you're the designer of that chip, you have to make assumptions about what sensors do I have and what data do they feed me, how much data do they feed me, and then you design a chip. So and then the old, still very current, but in the classic approach, as a chip designer, you design this chip and you have to do this before serious development of the vehicle starts. And it might always happen that by the time you do road testing or virtual road testing, then you find out, oh my God, we don't have enough compute power on this chip. And at that stage, it's too late, and redoing this whole design is extremely expensive. So what I'm talking about is the next stage is where we can enable a designer, and we actually already do this at Siemens at some level, where we say at the pre-silicon level, so at a stage where you haven't even made that chip, you are already able to validate the functionality of the chip in a simulation environment that can include a driving car on a road that sees people walking by and that sees a red light and everything else, so that you're able to make sure that what you're designing here that will be later become a physical chip can do the job the way this vehicle is designed. That's kind of the next level we are talking about.
Annie, given your deep experience with digital twin concept in manufacturing for many years, what is your projection? What do you say in the future? Like, what are the future trends in this technology, say over the next 3 to 5 years?
We are all doing the heavy duty work to create a digital twin. But for the users of digital twin, it should be super simplified. So in the next few years, I continue to see that we, as the digital twin developer, we continue to put in a lot of effort to make it work, to make the data flow nicely so that we can get the data at our fingertips. But at the same time, maybe in a few more years later, I expect our users to be able to interact with digital twin as a person. This is where the intelligence twin will come into play. This is where the AI will come into play when we talk about digital twin. 5 years, 10 years from now, I do not want to launch digital twin application and start traversing down to a certain asset and start getting data. I would like to hold it and I say, hey, twin, there's a problem of such and such. Give me what's the performance in the last 30 days. The twins should be able to tell me, guess what? By looking into the last 30 days of data, I start seeing there's a bottleneck of such. That will be one scenario of the digital twin. What's more, if you start following the term, it's a data presentation to me, right? I also want to do the other way around. When I say, hey, Siri, make a phone call. I want to do the same thing to the twin. Hey, twin, close that particular light curtain for me or turn off something for me. We should be able to do the two-way communication within a certain safety protocol. So that is what I would see the future should reside for digital twin. It's an interactive twin as an assistant to us at work and in the personal world as well.
There are some recent concepts that actually build beyond the idea of digital twins. In fact, being motivated from the idea of digital twins, where we kind of create a digital replica of a product or a process. So extending this idea, there are some new concepts that take this beyond to connect the various other, functions in manufacturing. And one of these concepts is called digital thread. And you may come across the digital thread being used in some of the industry context, in presentations or in discussions in the future of manufacturing. Well, let's understand what is digital thread in manufacturing. Digital thread is an attempt to kind of build a seamless integration across various functions in manufacturing organization, right? We can talk about manufacturers as a business, then there are so many different functions. And manufacturing is just one of the pieces that they do. There is vendor management, there is quality, there is, engineering, and finance side of it, who actually contribute to design of the product. So it's the logistics and operations to kind of deliver the product or get the inbound, the supplier, into the manufacturing operations. So all these subsystems or the sub-functions, they actually connect to contribute to making the entire manufacturing, operation happen end to end. If you can think about a digital thread is something like, it's a concept that try to close the loop, close the gap across these different functions and do a seamless integration so that you have a common data model that actually kind of allows the exchange of information. And if possible, you can think in terms of providing a digital view of how these are connected so that you have transparency and actually you are moving towards creating what I would call as a single source of truth. Because often in manufacturing organization, what happens is each of these sub functions that we talk about, whether it is product management, whether it is engineering, whether it is manufacturing, or finance or vendor management, they often the processes that actually run these functions, they're often implemented in multiple systems, multiple software built over time, and hence they actually often become what I call as siloed pieces. And that silo and the lack of connectivity creates a lot of friction in smoothly operating a manufacturing process, right, for efficiency and quality. And so digital thread is an attempt to kind of bring us all together. In fact, recent survey from PTC shows that claims digital thread as a nascent technology concept that will be continue to disrupt all industries, and they predict that this market of digital thread applications, connecting these different functions in manufacturing actually will grow up to almost $2.5 billion, from almost less than 500 million right now. It is supposed to, expand 5 times in the next 4 to 5 years. And on the right-hand side of the chart from the survey, you can see that they also find that manufacturing industries are kind of lagging behind in terms of how they are adopting digital thread, where some other industries like automotive and technology industries are a little bit ahead. So hence, it is an opportunity. I think we may see these initiatives around digital thread connecting the different functions in manufacturing, more popular in manufacturing in the coming years. The digital thread, how is it implemented? Basically, in order to create this seamless view, the integration has to start with understanding the different software and systems and tools that actually run these operations, like some of the enterprise systems, like your enterprise resource planning ERP software, your customer relationship management CRM software, computer-aided design CAD software that captures the design information, product lifecycle management software that captures the information about the entire R&D process of developing a new product, all the different phases. It's all captured in that software. And of course, we talked about IoT and digital twin platform and software. So, ERP, for example, brings all the finance information, and the HR information, in terms of the talent that is deployed in various operations, all those information there. Now, think about connecting all these things seamlessly, right, through and making the data model, kind of common in a way that they can talk to each other, to build this one layer above for you to see a digital version of how the manufacturing plant is operating, how the manufacturing business is operating. So just to give an example, so if you go back to the electric motor, that you can kind of the electric motor examples, if you're a manufacturer kind of manufacturing and selling electric motors to customers, you have the ability to kind of track the motor at a customer premise, directly, or through kind of a sales and through CRM kind of software, coming into your digital twins application, really live information of how the customer is using, and the different parts in the digital twin being captured in CAD/CAM systems, and how that CAD/CAM software is capturing the digital information about the design of the parts. And then in the PLM system, where exactly how many prototypes were run, how many tests were run for that spindle that is used in the motor, so that if you have a problem, you can go and connect on that and see. And then, of course, directly connected to the ERP in terms of what was the cost of manufacturing that particular part, what additional cost went into it to take some steps, or is there any changes happened, what is the efficiency of the process at that point in time where this was manufactured, and also who are the people who worked on it. So you get an idea how you can capture all the operations, the information about that in one platform, to what we call as what would call as the digital thread of the entire manufacturing operations. That actually summarizes what this concept of digital thread is about. It is not going to be easy to implement, because it is always a challenge to integrate all these systems, but that's an attempt that some of the companies are into right now, to create that one single source of truth to aid effective management of manufacturing operations, and of course build business value for all the stakeholders in manufacturing. So let's revisit our learning objective that we started with in this course. So we talked about what are digital twins. We started with a simple example of a coffee mug to explain how digital twins work. Then from there we understood the difference between the static and dynamic digital twins in terms of the richness of the data they collect. Then we moved to discussing the application of digital twins in the manufacturing context and manufacturing industries, and we saw that. Video around digital twin of electric motor. We discussed, what are product digital twins, what are process digital twins, and we also, went into the details of the different layers of how you can make the digital twins more complex and derive more value. And then you recall the green box and the yellow box and red box, which is first starting with the static digital twin or just the design data. We combine design and manufacturing data. In the yellow box, and then we have the full dynamic digital twin, which is the red box collecting all the information in real time from the product usage. So we also discussed the different business benefits that you can get in manufacturing context by the application of digital twins. Specifically, we went into the auto industry and looked at specific uses of the product and process digital twins in terms of how they kind of benefit in manufacturing from that. And we discussed the usage of digital twins in autonomous driving and testing of the autopilot features. Then we actually gave a framework to understand the broader business implications and the business value propositions coming from digital twins. And then we moved on to understanding when these digital twin projects and initiatives are successful and what companies need to do in order to ensure that they have the right capabilities. We provided this 6-step implementation framework to ensure that these projects are implemented successfully. Then we moved on to understand some of the risks and challenges that companies are likely to face when they are thinking about deploying digital twins in their operations. Then finally, we moved to understanding the future trends in digital twins and technology. And then we also introduced what is now known as digital thread concept, which is it's kind of a nascent concept. A lot of companies are trying to build this digital connection to provide seamless integration across different functions in manufacturing, so that you can have full visibility across different functions end to end in a manufacturing context.